Welcome all to today's ASRG World Webinar. We have the 15th of April 2021 and we are streaming from Stuttgart in Germany. Thank you for being with us. First of all, let me briefly introduce myself. My name is Sven Schran and I am coordinating with ASRG our European locations. ASRG is now more than 3.5 years old and I joined a bit more than 2 years ago. I have worked in the automotive industry just for more than 13 years and started to take care about automotive security more than 4 years ago. Today, I fulfill a role as product security officer in engineering of complex sensors for the Robot Bosch Group, which is one of the biggest automotive suppliers in the world. Just quickly, the Automotive Security Research Group, or short ASRG, is a non-profit organization focusing on supporting the automotive security industry on the journey to the connected and autonomous mobility. It is an open community for you, the automotive engineer, the IT security specialist, the security researcher, the beginner, the hobbyist, even for the people that are in the wrong YouTube channel. The entire organization is built on volunteer efforts of the administrative team and, of course, yourself. ASRG is mainly based on 3 important pillars which represent our core values: sharing knowledge, enabling networking, and valuable collaborations. We are trying to remove the boundaries that can occur in the automotive security industry. This means, for example, communicating about relevant publicly available information, finding ways to learn together, finding good solutions, or making best decisions, because at the end of the day, we all together have a joint purpose: to keep our customers, our families, our friends' data safe and secure when they are using automotive-related products or services. And this can only be achieved together. If you want to get more involved, make an impact on the industry, start your own ASRG location, participate in a technical committee, or be part of one of our projects, please reach out to us. You find more about ASRG at our webpage www.asrg.io or send us just an email at hello@asrg.io. ASRG is just available around the globe. Today we are present in 41 locations in 21 countries and we just reached more than 6,700 members, which is really amazing. As our newest location, we welcome Pune in India in the community. On average, we have grown around 15% a month since ASRG was founded, and this trend still continues steadily. Please check out if your hometown is just part of our network. If this is the case, you are welcome to join our local representation. If you don't find a location near you for now, but think it would make sense to have an ASRG location in your city as well, don't hesitate and contact us. Before we come to our main presentation, I like to give an outlook to the next weeks where we have again very interesting topics which we will provide to you via our ASRG World Webinar live stream. On 22 of April, we have Sekar Kulandaiwal from Scilab at the Carnegie Mellon University, and he will talk about preventing attack kill chains with a better security test bed. 1 week later, we have Victor Marginan and Kamal Kumar Singh from Continental, and they gave a presentation about secure the supply chain. On 6th of May, we will have Matthias Weber from SecOps Solution, and he will talk about vehicle key lifecycle management. On 3rd of June, we will welcome Martin Moser from eScript, and he will talk to us about the 7 golden rules for successful security testing. And at least on 7th of June, we will have Derek from CAN Bus Dutch, and he talk about 2 wires and 2 wheels. Bikes can do, can too. If you think you have a topic as well which is related to security and automotive and you would like to present it to our community, please contact us with your idea via cfp@asrg.io. So now it is enough from my side, and I don't want to keep you tortured anymore because I'm sure you are waiting very curious for our main presentation. Like every time, in case you have questions during the presentation, please write it in the chat window. After the main presentation, we will have a Q&A session where we will ask Professor Kargl. And now it is my pleasure to welcome Professor Dr. Frank Kargl, the director of the Institute of Distributed Systems at Ulm University, and he will present to us misbehavior detection and reaction in connected automated driving. Frank, the virtual stage is yours.
You're welcome to this presentation. As announced, it's going to be about misbehavior detection and reaction in connected automated driving. My name is Frank Kargl, and this is work we are doing at Ulm University in the context of the German SecForecast project. If you ask yourself, where is Ulm University located? It's in the south of Germany, about halfway between Stuttgart on the one side, Munich on the other side, and there's also Ingolstadt close by. So we are kind of surrounded by automotive industry. And this is what made me already more than 15 years back starting to look into automotive security. We have in Ulm a comparatively large center of researchers that is called F3, and it's made up of researchers from engineering, computer science, and psychology that together look into various aspects of cooperative and highly automated driving. Now, as you are all aware, a modern vehicle is a very complex system with tons of electronics, electronic control units, dozens of them connected by all sorts of networks. And of course, it was just natural that eventually someone started to ask the question, what happens if this system gets attacked? And you all know that around the 2010, I would say, there were quite a lot of publications emerging from people like Karl Korscher and his group, or also people, for example, looking into the COMBOX of BMW, or the works by Charlie Miller, Chris Walasek with their famous Jeep hack. And around the same time, and also earlier, we've been involved in many projects trying to secure the upcoming car-to-car communication and other communication interfaces. This started as far back as 2006, when I was a member of a pan-European project called CEVICOM, where we investigated secure vehicle communication, as the name implies. Other projects then, like the European project Preciosa, focused on privacy in connected driving, cooperative intelligent transport systems. This was a national project. In Preserve, which we were doing from around 2011 onwards, and where I was the coordinator, we had a group of different organizations, as the name said, preparing deployment of secure V2X communication systems. We developed a security subsystem that was also available open source. We worked on a hardware security module based on a security ASIC that was shown here, etc. And then, while all these projects predominantly looked into the communication aspect of security, but more or less of traditional vehicles, since a few years, we now shifted focus a lot on connected automated driving. All these years, when someone asked me what are the ingredients to make a connected vehicle secure, I was basically showing this slide here. So you basically need three elements. The first one, ID management and integrity protection, basically ensures that if you have communicating vehicles, that each vehicle can be authenticated and the messages it sends can be integrity protected to make sure that only valid vehicles can participate in ITS communication. And let's say nobody can just take his laptop, stand on the roadside, and send spoofed messages. Then, and we do this essentially by equipping vehicles with certificates and making them sign their messages. The next question that arises from this is, as messages and thus vehicles become identifiable, how do we protect drivers' privacy? How do we prevent these vehicles from becoming trackable by some malicious entity? And this is why we came up with these ideas of changing pseudonyms so that vehicles would not use permanent identifiers, but continuously changing pseudonymous identifiers. Yeah, but even with these two elements in place, a manipulated vehicle that's, for example, infected by malware or has been manipulated by its owner would still be able to send correctly signed information or messages containing incorrect information. And this is where misbehavior detection, as we call it, kicks in. Basically, we want to prevent a valid vehicle from injecting incorrect data into the intelligent transportation system. And while the first two elements are, let's say, very well understood, or at least there are sound proposals, I would say, how to solve it. And this is also, let's say, baked into standards, be it the IEEE standards on the US side or the ETSI standards on the European side, for example. Yeah, this misbehavior detection, I think, is the area where there's still most area or most room for researchers like us. And that's why a lot of our focus or a lot of our works in the previous years have been focusing on this. And if you're interested to get a good overview over this area, I can recommend the survey that we have published in 2019 in IEEE Communications Survey and Tutorials, which gives you a pretty good picture on the research landscape in that field. So in misbehavior detection, we're basically not dealing with external attackers that we need to keep out of the network, which we can effectively do with certificate signing, etc. But rather, the attackers are part of the network. They are insider attackers that basically send incorrect information to other vehicles. And these are the attackers, the type of attackers that we want to detect with our misbehavior detection system and exclude from the network. Yeah, and and this is something very natural to us. We are basically doing that as humans. We are constantly evaluating information and rejecting information that we don't consider plausible or inconsistent with our previous knowledge. So if I, for example, would tell you, hey, look out of the window, there's a kangaroo. Now, if you're not happen to come from Australia, then you will probably simply not believe me. You might not even turn your head to check whether that's okay or whether that's really the case. Because, yeah, well, I mean, you will consider it very, very implausible that there's a kangaroo outside of your house, for example, here in Europe. Yeah, so you will immediately say, no, that's not plausible. I don't believe you. And these are the kind of mechanisms that researchers, including us, want to teach to our computers when we talk about misbehavior detection. And this is, again, the survey I was mentioning. And in this survey, we're basically categorizing the proposed detection mechanisms into various groups. The first categorization is along the lines of what is this mechanism looking at? Is it looking at the data contained in the message? Then we term this a data-centric mechanism. Yeah, and for these data-centric mechanisms can then be split further into plausibility checking and consistency checking. And I will come up with a couple of examples here. And on the other hand, if we don't look at the data, we can look at the node that is sending these messages, whether the node is trustworthy or not. Yeah, those would be trust-based mechanisms. And we can also look into how is the node behaving. Is it, for example, following specifications or not? Now, let me give you some examples for this. Let's start with a node-centric trust-based mechanism. The simplest example would be, if, for example, a vehicle or an attacker sends a message, so other vehicles receive a message that claims, for example, on this stretch of road, the currently driven speed is 0 kilometers per hour, so there would be a traffic jam. But if this message is not signed correctly, a trust-based mechanism would simply say, no, we cannot trust this node because this node does not hold correct credentials. It's not signing its messages appropriately. A behavioral mechanism would, for example, be a node or vehicle that would spam the channel with messages with a very high frequency. This could also be detected as a malicious node because it's not conforming to specifications. So that would be a behavioral mechanism. Let's look at the data-centric mechanisms next. And for example, if a vehicle would, in its messages, pretend to drive with 500 kilometers per hour, this surely conflicts with our physical models, how vehicles behave. There are very, very few vehicles that can achieve these speeds, and you typically don't find them on public roads. So a plausibility checking mechanism would reject such a message or such an information rather as implausible. Then you can also have consistency checking. For example, you can check the consistency of information you receive via communication. If this vehicle here pretends to have to stand still, 0 kilometers per hour, you could check that with local sensors. So if your radar tells you this vehicle is clearly moving forward, then it's an inconsistency that your misbehavior detection system can discover. But what would you do if you have a vehicle that's outside of your local range? So this vehicle here pretends to drive at 0 kilometers per hour. Well, if you have if other information from the same area can reach you over node disjoint paths, so this vehicle here is able to send you information via multi-hop forwarding to that vehicle, and this information cannot be manipulated, for example, filtered out by this attacker, because it's a second redundant communication path available. Then again, we have the opportunity for consistency checking. And this work on misbehavior detection and finding these kind of mechanisms already dates back a long time. So this was, let's say, or this type of research started in the early 2000s. And for example, in some of our papers, we proposed very simple detection mechanisms like an acceptance range threshold that would compare the positions in these beacon messages, the claimed positions where a vehicle would be with the typical communication range. And if a vehicle pretends to be at a location far outside of the communication range of the receiving vehicle, that would of course then be, or this information would be rejected or considered less trustworthy. Other sensors would, for example, look at the mobility patterns of vehicles, and if the reported positions in subsequent messages from the same vehicle would have a very odd movement pattern, these kind of messages, this kind of information would be rejected, and so on. In simulations back then, we could actually show that even such single mechanisms are quite effective against specific types of attacks. Yeah, so you have pretty good detection rates, very low false positive rates, depending on a number of factors and parameters like the vehicle velocity, of course. But overall, these detectors perform quite well if you go and want to detect a specific attack. But then if you have other forms of attacks, other forms of misbehavior, of sending incorrect information, such a specific detector may be completely useless. And this led over time to more and more complex misbehavior detection systems. I show here a diagram from work by Hagen Stübing and Norbert Bismeier that they did at TU Darmstadt together with Opel. And yeah, basically information received by a vehicle would undergo all kinds of checks, including Kalman filters and tracking the movement of vehicles, maneuver recognition based on Bayesian networks or Bayesian based mechanisms, etc., 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 to be able to decide whether information should be rejected or accepted. The problem with these kind of frameworks is that they are tailored very carefully on the specific types of detection mechanisms you have, and also the sequence of these detection mechanisms here play an important role. And you see this becomes quite complex. And then if different types of attacks are discovered, you want to add more detectors, additional detectors, this gets quite complicated and very inflexible. This is why in our research over the past years, we came up with a misbehavior detection framework that we call Mart, where the core idea is that an arbitrary number of different detectors can be combined. These detectors would look at data that is stored in a world model, and we then use what is called subjective logic. That's a probabilistic logic to reason in the face of uncertainty, to basically take all the different outputs of all the different detectors and fuse them together into a specific rating of information. And I want to go a little bit deeper into that and introduce you a little bit to this subjective logic, which was originally developed at Oslo University in Norway. So the core concept of subjective logic is what is called an opinion. So basically, such a misbehavior detection framework would form an opinion over a specific piece of information, a specific statement. This is done using a belief function. So basically, you can have a multi-valued statement that about a certain fact X, and the belief function would give you the belief based on evidence into the different possible values of X. You also have an uncertainty value. Basically, this allows you to express how sure you are based on your evidence that your calculation of belief is correct. And you also have an a priori knowledge that you can represent as the space rate A. So that is basically the probability of a certain X in absence of further knowledge. Now, while this X can be have a multi-value domain, what we typically do is we simplify this to a binary domain where a statement can either be true or false. This makes all the calculations easier. And what our Mart framework is essentially doing, it's basically taking information and it rates whether it thinks this information is true or this information is false. All this while also considering the uncertainty in this judgment. Now, in Mart, every detector, and there can be an arbitrary amount of these detectors, can basically provide such opinions that would also be stored in the word model on the same piece of information. And then there are different fusion operators that allow us to take multiple of these information and integrate them into one joint opinion that can then be used to decide whether this information should be used by applications or not. I have some more details here about this subjective logic when used in binary domains. I would rather skip this and show you a simpler intuition of what such an opinion would be. So such an opinion of an opinion holder A, which can be a misbehavior detection mechanism that forms an opinion on certain data, whether this data is true or not. For example, if a vehicle sends its position, whether the vehicle is actually at this position or not. And this opinion can be represented also graphically as a position within this triangle, which basically either has a belief or vice versa, a disbelief if you believe it's true, and this uncertainty. And depending on where in this triangle your opinion is located, for example, you can express that you are 100% sure with no uncertainty that this fact is true, then you would be here. Or the opposite, if you are 100% sure that this information is incorrect, that the vehicle is not at this position, then you are here. Or if you are, for example, have an opinion here, you simply don't know beyond the base rate whether this position claim is true or not. And the sum of belief, disbelief, and uncertainty would have to sum up to always to 1. What Mart is now doing, it's basically taking this data in the word model where vehicles make statements about, for example, their position. And now it takes all kind of data-centric detectors and node-centric detectors that form opinions on either the vehicles, if it's node-centric, or the data when it's data-centric. And you then use these fusion mechanisms, these fusion operators, for example, to calculate a trust value. For example, if a vehicle has an opinion on another vehicle that has an opinion on the data, you can basically calculate this transitive opinion path here to come up with an opinion of this detector on this, whether this data is trustworthy or not. And if you have many detectors, you can just fuse all these different opinions into one value. And this constantly happens inside Mart, so that in the end, the applications that want to retrieve certain data and use certain data from the world model can also be provided with an assessment of the trustworthiness of data. And all this research, including our research on Mart, started with looking into car-to-X communication. So it was all about communicating vehicles driven by drivers, and the decision here was basically that only, for example, trustworthy data should be signaled to the driver. Only warnings that are trustworthy should create a warning to the driver, etc., etc. But of course, with this emerging trends to higher degrees of automation in driving functions and fully automated driving, it was kind of natural to take the next step and look at not only communicating, but communicating and automated cars and their security. And we took this step a few years back when forming the SecForecast project. It's a German nationally funded project with a total of 14 partners, as shown here, from academia, but also from industry. And what we essentially do in this project is we look at a broad variety of challenges and research questions surrounding the special or the novel aspects of automated driving for security. Yeah, so essentially we say, okay, such an self-driving car has a quite complex data processing and also complex control algorithms embedded. It has a broad range of sensors, but of course it also communicates with nearby vehicles and infrastructure, and it also retrieves a lot of information from remote data sources. But in the end, it uses all this data to fuse it together to create a perception of its environment, and then moves on to make decisions based on this environmental perception, plan its trajectory, and make the vehicle move according to this planned trajectory. Now, if you again take the step and postulate an attacker to such a vehicle, of course you can come up with this attacker manipulating the communication as we have assumed earlier. But of course, the attacker could also try to attack the sensors, the radar sensors, the LiDAR sensors, and it could also try to manipulate data sources. And of course, it could also try to hack into the car and manipulate these functions here themselves. And assuming such an attacker, it's not sufficient to just detect a misbehavior, to detect incorrect information, because there's no driver that you can warn and that can then control and adjust his driving to this. You would also inevitably have to take the next step and think about how would the automated vehicle then react to such misbehavior. And we've taken first steps a few years back when we looked into how to secure cooperative adaptive cruise control and also look into what a kind of damage could an attacker do in such a system. Cooperative adaptive cruise control is a very simple automated driving function which makes it very accessible also to research and analysis. Sometimes this is also called communication-based platooning. The idea is you have a leader vehicle and your follower vehicles, and you want them to form a platoon and drive at controlled and close distance to each other. The leading vehicle would send communication to the following vehicles, and they would of course then forward this information and also add their own information, and based on a control algorithm they can then form such a platoon. If we now assume an attacker, so let's assume this vehicle V0 is an attacker, this vehicle could of course send incorrect information to the followers. So it could, for example, simulate an emergency brake, signaling a very high deceleration. And the question is, how would the platoon as a whole, and in particular, of course, the immediate follower V1 here, how would V1 react? It would probably also start to brake sharply, and that could lead, for example, to rear-end accidents, V2 crashing into V1. And as said, we were analyzing this already some years back. This is a publication from Vehicle Networking Conference 2017. And essentially there we could show in simulations that with the standard control algorithms, this can indeed lead to accidents and quite severe crashes. We then, of course, postulate that misbehavior detection and misbehavior reaction can mitigate the attack can prevent accidents and crashes. And that was what we were investigating in the following years. And we had another publication at VNC 2020 just last year. And what I'm presenting now is also taken from this publication. Yeah, so the system model we had here was basically, we have this world model that's fed with information on the one hand from the network, on the other hand from sensors. In that case, we looked into radar sensors. And yeah, normally this data from the world model would be made directly available to the cITS controller, which would then control acceleration and deceleration of the vehicles in the platoon through the ego controllers and the actuators. Assuming attacks, the other data path would basically be that the data is first fed into the misbehavior detection system, and the misbehavior detection would either rate the data regarding its trustworthiness or even filter untrustworthy data out so that the cITS controller only sees trustworthy information. In our 2020 paper, we basically then discuss the design spectrum of such a system, how misbehavior detection could be incorporated into such a cITS system. Yeah. On the one hand, we could basically make the system rely in its reaction to misbehavior mostly on the misbehavior detection system. So the misbehavior detection system would modify the input to the cITS controller either by dropping false messages completely or by modifying the estimates and the input for the controller, or noise shaping would be another option. Or we could even try to go completely without misbehavior detection by just making our control algorithm more attack resilient. And there's also a kind of a middle way where we basically take the have the misbehavior detection system calculate what we call the suspiciousness parameter that expresses how untrustworthy data is, how likely the vehicle is currently under attack. And then we have two reactions. Either the car falls back to ACC, so it does not rely on external information anymore, just implements platooning based on, for example, its own radar. Or we have a controller that can directly react to the suspiciousness parameter and adjust its behavior based on this parameter. And this is a new proposal we made in this paper, and I want to show you a little bit how this performs compared to the plain case where there's no misbehavior detection at all, or the case where we have a fallback to ACC. So what we are comparing is the attacker that injects fake acceleration data into the system. Strategy 1, that would be the baseline, is we don't have misbehavior detection at all. All the data is just forwarded to the plain vanilla cITS controller. We were doing these simulations with a simulation framework relying on the OMNet++ simulator, extended by a package for Car-to-X communication, and also called VANES, that also includes Sumo for the mobility modeling, and an additional framework called Plexe that implements different of these cITS algorithms. So this would be strategy 1, this would be our baseline. And we compare this with another strategy where, in the case the misbehavior detection detects an attack, we would immediately fall back. So here an attack is detected, we would immediately fall back to plain ACC and would not consider the fake information here at all. And last but not least, we have this new strategy with suspiciousness parameter and adjusted controller reaction. So in case such an attack is detected, the data is forwarded to the cACC controller, but together with the suspiciousness parameter, which has a value between 0 and 1, and the cACC controller will take this into consideration in calculating its safe distance to the predecessor vehicle. Yeah, we visualized the outcomes of all these simulations in such graphs here. So basically, we have our attacker inject fake acceleration data. So the platoon was basically driving at constant speed. So acceleration of 0 meters per second square would be the standard speed. And yeah, the fake acceleration could have a range from 2 meters per second square all the way down to a deceleration of 9 meters per second square. We also looked at different speeds at which the platoon was driving, 50, 100, 150 meters per second. And what these diagrams basically show is the, in case of these blue boxes, the driving distance at which the platoon stabilizes. Yeah, so basically here you can see that for the correct values, the platoon drives at a distance of 5 meters apart, all the way to 7.6 meters. If we go to these red boxes, this basically means that an accident happened and the value in the cells represents the speed difference at which this accident happened. So higher values means harder crashes. Now, if there's no misbehavior detection at all, you see that the algorithm can cope certain fake values, but this will lead to the platoon driving at larger distances. But for, let's say, stronger decelerations, there will be crashes, so vehicles will not be able to, the following vehicle will brake sharply and the subsequent vehicles will not be able to avoid a crash. Now, if we now implement a misbehavior detection that would detect as soon as the attacker starts sending fake acceleration data, in that case, the system would immediately fall back to ACC. It would ignore all the data from the attacker sent via the network, and you see that in ACC mode, as this data is ignored, we will have a safe platoon with a constant headway, with a constant distance. And you also see that this distance, of course, is in all cases larger than what in the optimal cACC case with no attack is achievable. So we have an efficiency loss in our platooning application, but we avoid accidents. If we go to this strategy with suspiciousness parameter, so the strategy has certain parameters, T noise and T misbehavior, that we have configured here to some values. You see that for mild faking, where the fake acceleration data is at least close to the real value, we can, on the one hand, avoid all accidents, and we can also keep comparatively close distances. But for the rest of the value domain, so in particular if there's strong fake deceleration, we are basically not better off than the fallback to ACC. So our strategy basically degenerates to the fallback to ACC. But at least for, let's say, mild misbehavior, there is an advantage compared to the direct fallback to ACC strategy. We can extend this range here by tuning these parameters so that the benefit of cITS over ACC can be maintained even for stronger attacks. The problem is that at some point we will also see accidents again. And this is what we're currently investigating, this trade-off of these parameters and how to optimally tune them, on the one hand to avoid accidents, on the other hand to gain maximum benefit. We're also implementing this in a little demonstrator based on such toy cars. Can just start this here. So you basically see this cars here on this track driving, forming a platoon, driving in cITS mode. This goes on for a while, and at a certain point we will then have an attacker injecting fake acceleration data into the system, and you will then see how the platoon becomes unstable. This should happen somewhere around now. Now it's still going on a little bit. Okay, now you see that, well, there are at least kind of crashes here. And we are currently about to implement also the misbehavior detection system in this demonstrator to show how this can be avoided. Yeah, so with this research, we want to take the step from misbehavior detection to reaction so that vehicles can defend themselves automatically from this kind of fake attacks with incorrect data. We have a broad range of broad design spectrum where we have started to investigate first options, but there's also a lot that we want to still do on attack resilient control or also this modified controller input. So that's what keeps us currently busy. Yeah, the SecForecast project is, as said, working on a broad range of topics. So this cITS misbehavior detection is just a small slice of the overall spectrum. For example, SecForecast is also working on methods and tools for safety, security modeling, and risk analysis. One result is a threat modeling tool that can help penetration testers to focus their attacks and penetration testing to the critical parts of the automotive system. This TMT-E4PT is also available open source. We're working on attack use case visualization. We have a lot of other works on attacks and penetration testing. For example, a system that tries to automate ECU security testing, interface testing. We have quite some interesting work on attacks on radar. We have now almost ready a fuzzing framework for some IP. Another topic is how to conduct responsible disclosure in the automotive domain, etc., etc. We're also working on novel security mechanisms and concepts. For example, relying on physically unclonable functions, secure sensor data fusion is a topic. And we also look into how to integrate these misbehavior detection systems I spoke of with the in-vehicle intrusion detection systems. Yeah, and SecForecast is just one step. We are extending this research together with Japanese partners. So parts of SecForecast are now also collaborating with Japanese partners in a project called SAFE, where we want to join our expertise and look, for example, at supply chain security and similar topics. Yeah, with this, I conclude the talk. And if you have questions, I invite you to just send me your questions in email to frank.kargl@uni-ulm.de, and I will come back to you as quickly as possible. Thank you.